Hey everybody, this is Nick Kushner. I'm going to be discussing some guitar physics with you today. I made this poster called The Physics of Musical Sound a long time ago. It kind of like summarizes a lot of important things that I'd like to talk about. First I want to discuss some wave mechanics. So what is a wave? Here's a diagram that you may have seen that defines some wave properties. Before I get into that, it's important to note that this diagram is a mathematical representation of a wave. When waves travel in air, you do not see this sine wave. A wave is caused by a vibration or a disturbance from a normal resting state. So this line here represents the normal resting state. This can actually be viewed as a string, and so the string at a resting state would be here, and if you cause a vibration, then you would have this kind of like displacement here, here, and it has peaks and troughs. So these are the peaks, and these are the troughs. There'll be a trough there, and for a wave in air, the peak is the maximum compression of the air molecules, and the trough is the maximum rarefaction. Points in between would represent varying measurements of air compression. So there's a point in between here, or a point in between here. It's important to note that waves in air or on a guitar string travel similarly to how dominoes seem to move when you place them one after another and then push one down. The particles move a short distance and impart their energy to the adjacent area. So waves have the following properties. The period t is the time in seconds between two successive peaks. So the time between here and here can be viewed as the period, or from this point to this point. Frequency f is the number of peaks per second, and it's equal to 1 over t. So this would be a peak, and how many peaks travel in 1 second is a measure of the frequency. An example would be A440. All 440 means is that in 1 second 440 peaks go by. The unit of peaks per second is called hertz. So the open A string on a guitar has a frequency of 110 hertz. If you play the A 12th fret, which is an octave above the open A, that has a frequency of 220 hertz, which is double. So that's an important thing to know, that the frequency doubles when you go up an octave. And it's important to note that the frequency is a physical measurement of pitch. So higher frequency is associated with a higher pitch. The wavelength, which is denoted by lambda, is the distance between two successive peaks. So it could be the distance between this peak and that peak, or you can also view it as a distance between this point and this point here. So where it goes through a peak and a trough, and then it comes right back to where you started. That is the distance between here and here would be the wavelength. The amplitude, denoted by h here, this is h and then minus h, represents the maximum displacement of the varying quantity from its average value. So the amplitude pretty much determines how loud the wave is. Here, this is the law of Pythagoras. The period of a free vibration is proportional to the length of string which vibrates. So what does this mean? It means that in order to get higher notes on a single string, just reduce the length of the string that vibrates. Guitarists do this by fretting higher up the neck to make a higher pitch. That's pretty basic. This is V is equal to F lambda, the velocity. the velocity of a wave is equal to the frequency times the wavelength. And here I give units. The velocity of the wave in meters per second is equal to the frequency in number of wavelengths per second times the wavelength in meters. So meters per second will give you a velocity. From a guitar point of view, the velocity of a wave on a string is the speed of the wave traveling on a string, and strings that are lighter and have more tension generate waves that travel faster along a string than a heavier string with less tension. There's another velocity equation. This one here, velocity is equal to the square root of the tension of the string divided by m, which is mass per unit length of the string. And that is derived, it's called the wave equation. And that equation is derived from Newton's laws and involves the use of partial differential equations, which I won't go into. Right here, the frequency is equal to the velocity divided by 2L. And L would be the length of the string. That's pretty much a manipulation of this equation here. V is equal to F times the lambda, where the wavelength, and in this case, the wavelength is, in equation 2, is equal to 2 times the length of the vibrating string. This will become more clear when I talk about harmonics, and that'll be in the next video. So hope to see you then. Okay, bye.